Okay, so this is tutorial part 4 for the simulations tutorial. In this video, I'm going to show you how to use the model that we used in the last video where we modeled the wheel and basically use that to drive simulation of our rover. So actually getting a rover body into our model and then setting up our drivetrain as well. So all the gears, and we're not going to do the motor in this video, but in the next video we will be doing the motor. So first, before I start this video, if you want to grab the files from the last part so you can follow along, just go to the description and follow the GitHub link to part 3. Grab those files and you can get started. All right, so I'm going to hop over to our wheel model here. So this is the model that we had last time. What we're going to do now is we are going to add something called a vehicle body block. Now, the purpose of this block was originally for doing car bodies and basically making simulations for cars. But we can tweak this a little bit to make it work in the way we want it to for like simulating a rover. So what we're going to do here is connect up this H import to our translational motion signal. What that's going to do is just feed a translational motion into the rover, which is going to then move it. So this V output here is the translational velocity of the rover. So if I just add a PS to Simulink converter, this output is a PS type, so we have to feed it in the converter and then feed the converter into the scope block here. So if we just run this, we can see the output of what the sensor is seeing. So one thing I forgot is before you actually run the model, remember that you have to go and declare the variables. So we have to run the edit vars script there and just get the variables loaded into the workspace. Okay, so let's try this again. Load this up and run the simulation. Okay, so you can see at time 2, that's when we step up our torque. And this red line here, if we go to measure, you can see that the red line is coming from converter 2, which is the third converter that we placed. And the first converter that we placed was the velocity. So sorry, that is the yellow line. So because you can't see the yellow line, that means the red line overrode it. So the output of the rover itself is giving the exact same output as the sensor is getting. So we now don't need the velocity part of the sensor. We can still use the position, as you can see, like the blue signal here, we're still getting the position. Now, another thing that you might notice is we are now getting speeds in micrometers per second. That is because our wheel has very little torque on it right now. So trying to push this great big rover, it's not really going to go anywhere. The wheels are going to be spinning a lot, so you're not actually going to be pushing this thing. So what we're going to do is next we want to go into the rover body here. Okay, so in here we got a bunch of variables that we can use. Here we're only really interested in 2 of the variables. This one here, gravitational acceleration, obviously don't have to change that because for our case, we're doing our rover on Earth. We're not actually sending it to Mars. If you were actually sending it to Mars, I guess you could change the gravitational acceleration a little bit. That would make it a little bit more accurate. But in our case, we're going to be running this on Earth, so we don't have to change that. And the mass of the rover here, we can actually specify as a variable like we did last time. So we're going to call this mass and mass of rover. So now that we have this specified as mass of rover, we need to set up the mass of rover variable. So we'll go into our edit vars here, set mass rover, oops, and we're going to set this equal to 50. So this is going to be the mass of our rover, which is 50 kilograms. So now you can see mass rover, 50 kilograms. And then we're going to set up our drag parameters. So just basically, if there's going to be any headwind, this is going to be the force that is opposing the rover as it tries to speed up. So the front area of our rover, we're just going to call area. And the drag coefficient, we're going to just estimate this as our rover to be a perfectly rectangular box. So the frontal area of the box is going to have a drag coefficient of 2.1. You can look up these drag coefficients online, not too hard to find. Now we have to specify area, and we're going to specify it as 0.6 meters squared. Now we're going to go back to um, our model here. Oh, and that's red, so we do have to run edit vars again just to set the variables. And when we run this, it won't get mad at us. So now let's run this again, see what happens. Okay, so now you can see we sped up a little bit because the mass before was about 1,000 kilograms. Now we have dropped it down to 50. So we are actually speeding up a little bit more because the tires are able to push it. Next thing we want to add in is a headwind. So we're going to set up a PS constant. So this is the exact same as a constant block like we were using before. But this is giving us a physical signal instead. So we actually don't need a converter for this one. We can feed it right into the block. So we're going to feed it into this input port here called W. That's the headwind. And we can set this variable to, let's go wind speed. And we're going to set the units to meters per second. And now we're going to go and set up wind speed. I'm going to set that to, let's say 1 meter per second right now. Remember to call edit vars to edit the parameters. And there we have it. Now we have a rover that is facing some headwind right now. So we can see what that's going to look like as our output. So now this looks really different. You can see before the torque is even applied, the rover is moving backwards. So the headwind is pushing the rover backwards. And then when the torque is applied, it's trying to oppose the headwind, but it's still not enough to get it to move in the forward direction. So the speed here in red, it did start to decrease slower. So you know that the wheel is trying to accelerate. It's just not enough to overcome the acceleration of the wind yet. Okay, so the next thing we're going to do is this NF and NR output signals, they're not really important to us. That's if you were building a car and you had specified axles. This is basically adding normal forces to each axle. So depending on how the car is starting and stopping, it just applies different normal forces to the back and the front axle. We're not going to do that for our rover because we don't actually have axles. We have suspensions that have 3 different legs on them. And then 2 sets of suspensions, so 6 legs total, each with 2 wheels on them. So it's not going to work the same for us, especially using a rocker bogie setup. It's not going to be the same as like a regular vehicle. But anyways, we're going to set up a beta. So the beta is just the incline of the train that you're trying to traverse. So we're going to set up a constant block. We're not going to make it a PS constant block yet because we still want to add a gain to it. Just because we want to specify this block in degrees. So say we want a 15-degree incline. We now have to convert this into radians. So pi divided by 180 because the rover body here is going to take the input in radians. So we just have this pi over 180 to convert to radians. And then we need a Simulink to PS converter and send that right into the beta. So now if we go ahead and go back to our variables, if we're going to set wind speed to 0, actually let's specify the angle too. So let's specify the angle to 15 degrees and just load back up here. Change this to angle. Oh, and we also have to make the changes. So make the changes. And now we can run our model. Okay, so as you can see, we have no headwind because I did change that, but we are going down a slope. So you can see right here, let's check out the slope of the velocity to start with. So the slope of our velocity is around, well, it should say negative 2.4 meters per second squared. So that is a fraction of the gravitational pull on the rover, which is what you would expect on an incline. And after 2 seconds, this is when the tires kick in and actually start rotating. We are now changed to 1.8 meters per second squared. So we're still going down the hill, but we're going down a little bit slower because the wheels are trying to oppose the rover going backwards. Okay, so the next thing that we are going to add is something called a magic formula tire. So if you just look up tire, you can actually look, there's 3 different kinds of tires. There's friction parameterized, there's tire, and then there's the magic formula. We're going to use this one for now. It's the simplest one to use other than the simple tire. So this tire does not take into effect any sort of like rotational resistance or effects of normal force on the wheel, any deformation based on the mass itself. And it also doesn't take into effect traction either. It does this solely based on torque and what it's pushing. This magic formula tire, we can actually specify how our tire interacts with the ground using different parameter values. So I'm just going to delete this simple tire here, and I'm going to move it into here. So now we have our magic formula tire, and I'm going to go into the parameters for it. So the first thing we're going to want to do is go into geometry. We got the radius set up, so we're going to set this to radius. Then we will go to dynamics. There's no inertia setup. We want to specify the inertia, and this is going to be 0.5 times mass times radius squared. Now, just to give you a quick look at what our tire setup is, this is just one leg of our suspension. So one leg will support 2 tires, and it's driven by one DC motor here. So what we actually want to do is we want to change this to not be 0.5 times the mass times radius squared, because that's only for one cylinder. We're actually driving 2 cylinders, so we can get rid of this 1/2, because we would just really multiply all of this by 2. So now this is our inertia for the 2 tires. One more thing too. We have to go here, change this to constant magic formula coefficients. And just from a quick research, I found that a car tire on wet tarmac is probably a good estimation for our tires and how they would interact with the ground. So I found the formula for coefficients for it, and it's 12, 2.3, 0.82, and 1. And you can change these coefficients however you need. It's super complex, the magic formula. It's very hard to determine the coefficients for a wheel. So basically, we're just going off of already researched numbers for car tires, and we're just looking at the ones with the least traction, somewhat reasonable tractions for our purposes, because we don't really want to try and determine ours empirically. So close this up, and now we have our tire set up. So another thing that we have to do with this tire is it's got one more input port here. So we actually have to specify the normal force that's affected on this tire. So like I said before, we have a suspension with 6 different legs. So the body's mass is going to be distributed, and we'll say, just as an estimation, will be distributed evenly over all the legs of the suspension. So we're going to set up a PS constant block. And in here, we are going to specify mass of the rover, and then times 9.81. So that's going to give us the rover's weight in newtons. So we'll change this to newtons. And remember that I said it's going to be split evenly over 6 legs, so we're going to divide that by 6. So that's the effective normal force acting on the tire. We're going to connect those up there. And this output here is basically to track slip. So it will give numbers based on like how much the tire is slipping. That's not really too important to us because it does come into effect with how the rover moves itself. We don't really need to see how much the tire is slipping. We just need to know the effect of the tire slipping on the rover. So what I'm going to do is I'm going to set up a PS terminate and set that right here. So that's just going to terminate the signal so that we don't get any problems later on. Okay, so now I want to go back here and let's say I want to set the angle to 0 now. See what this does. And we're going to open up the scope. So now we have our magic formula tire. We're just going to see how our simulation looks now that we have no incline and no headwind. Something's not right here. Angle and speed. Okay, just give me 1 minute here to debug what's happening. I'll be right back. Okay, so I found the problem. It turns out I changed the angle value here without actually updating the workspace here, so I didn't run the edit bars command. So don't forget to do that. That can be very annoying to try and figure out. Okay, so I'm just gonna run this again with the proper output. Okay, there we go. So no angle, no headwind. This is what we've got going on now. So as you can see, just reading from converter 2, so this is the rover body's velocity output. We're getting up to speeds around, let's see, what we're maxing out at around, getting up to like 15 millimeters per second. That's nothing special. It's pretty slow still. So that's mainly attributed to the fact that this tire is slipping a lot. And it's not able to push the rover. It doesn't have a whole lot of torque, so it can't actually move the rover's body. So what we're going to do now is we are going to add some gears. So you can step up the torque a little bit. It's going to lower the speed of the rotation of the tire, but we need the torque so that our tires stop slipping. So if I actually bring up this model again, and I'm just going to full screen this. So this is our model for the wheel and the wheel housing. So as you can see here, like this is our DC motor, and these are our two wheels are attached on the same axle. This is a gearbox. It's a 100-to-1 gearbox that basically steps up the torque from this DC motor. So as you know, as you step up the torque, the angular speed is also going to step down by the same amount. So as we step up the torque 100 times, we're going to lower the rotational speed 100 times. Now, another thing we have hidden in here, just 1 second, hide selected. Okay, we have some bevel gears hidden in here. So these bevel gears are just what changes the direction of the rotation. So going from this horizontal axis to this vertical axis. So another thing to point out is these gears have a 1-to-1 ratio. So you'd think they wouldn't have any effect on our torque or our speed, but these will be 3D printed bevel gears in our design. Those do have an efficiency. So they don't actually work as well as perfect gears would. So we have some sort of efficiency loss in them that we have to specify. So in our case, we're just going to guess at what kind of efficiency we're going to be outputting from that. So to add in these gears, we are going to type in gearbox, and then gear, and we're going to go to simple gear. So these simple gears will just act as our bevel gears, and this gearbox will be our 100-to-1 gearbox. So I'm going to move all of these over here, take this out, and I'm going to attach the gearbox and the bevel gears here and to the tire. Just going to shift this back over. Okay, so now we have this torque source, which we are kind of just estimating as our DC motor right now. That is going to then feed into our gearbox, which steps it up 100 times the torque. So we have to go in here, the gear ratio is 100. So that is going to step up the torque 100 and step down the rotational speed by 100. and then it feeds into our bevel gears. So the bevel gears we specified as a 1-to-1 gear ratio, so it's set to 1. We're going to change this so that's in the same direction as the input shaft. And then we're going to go to meshing losses, turn on constant efficiency, and we'll just keep this efficiency for now. We're not entirely sure how efficient our gears will be. This is just so that we have some sort of number, so that we have some sort of frictional losses or meshing losses in our gears, just to have as a parameter later on if we wanted to change that. And then that feeds directly into our wheel. So now our wheel should have a lot more torque going into it, but it will be rotating a lot slower. So with 0 angle and 0 headwind, let's just see what we are looking like now. Let's expand this a little bit. Okay, so now you can see our acceleration has increased quite a bit from the last time, and so has our speed. So that might seem counterintuitive. I did say that the rotational speed is going to decrease a lot, and it did. It's just what's happened now is that we have a lot better torque. So now we are actually rotating this tire with very little slip. We're still getting some good torque. We got some friction on the wheel, so we're actually able to push this Rover and not get any sort of slip or backlash in the gears. So that's why we are moving a lot faster now. If we had some different gear ratios, maybe we'd be going even faster. So if we lowered the gear ratio of our gearbox, it's possible that we could go faster just because our rotation speed wouldn't be reduced, but our torque would also be reduced. So we might actually still be slipping. Okay, so now this is basically our setup for driving the Rover. There's not too much we have to change, but I am going to show you what happens now if we change our headwind speed to 1. So do that, run edit vars. So before, when we had a headwind speed, we were going in the opposite direction. So the wind was pushing the Rover. Even with the tires moving, we couldn't go anywhere. So now let's see what happens when we have our headwind. So we are actually going forward now. So with the up torque to our wheel, we have a lot more power going to the wheel, and we're able to overcome this headwind speed. But if you actually zoom in here, you can see, I'm just going to change this. Okay, you can see that that we initially started off going in the opposite direction. So starting at 0 from time 0 to 2, which was our step time, the torque source wasn't applying any torque, so the headwind was actually pushing us backwards. So you can see our position here, slowly starting to move backwards. We're gaining momentum. We're going faster, 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 and then all of a sudden our motors kick back in. So our backwards velocity is increasing, and then all of a sudden our motors kick in and we're going forwards. So we check this out, and you can see that we are finally going in the direction that we want and slowly getting up to speed. So that's what we want. That's what we were hoping to model. So now we have something that actually resembles how our motor would be moving. Now this is only with one tire right now. So what you can do is basically just copy and paste this. We have 6 of these setups in our suspension. So what you do is just put 6 of these in parallel, connecting up the physical signals all together, and then connecting up the grounds all in the same place. So the solver is connected to all of the torque sources. And then the outputs here for H are all going to connect to this same line. You don't need any more of these sensors. These sensors basically useless now that we have this Rover body. And then you can connect all of the N imports to the same PS constant, have them all set up in series, and that will be a more realistic setup, more visually correct setup for what we have on our Rover. So I'm not going to actually do that right now. I'll do that off recording and I'll have it all set up in the next video. I will make the changes to the model for the GitHub. So the part 4 model will actually have 6 of these all in parallel. So you can grab that from the GitHub if you want, so that when you go into the next video, you won't have to catch up. All right, so yeah, just remember to grab the GitHub and I will see you in the next part.